Good morning, everyone, or good afternoon, depending on which time zone you're on. And welcome to the 53rd annual meeting of the Division for Planetary Sciences of the American Astronomical Society. I'm Shantanu Naidu. I'm the DPS press officer. And with us today are also Susanna Kohler, who's the AAS, incoming AAS press officer. We have Kerry Hensley, who's the deputy AAS press officer, and also Rick Feinberg, who's the outgoing or the past AAS press officer. So we're going to be recording this briefing and live streaming it on YouTube on the AAS press office channel. We have 4 exciting talks today. First off, we'll have Colin Chandler from Northern Arizona University who'll talk about recurrent activity from a main belt comet. Second, we'll have Henry Hsieh from the Planetary Science Institute who'll be talking about the nucleus and dust tail of an active asteroid. Next, we'll have Elliot Young, who will be talking about more evidence that Pluto's atmosphere is freezing out. And then we'll have Teddy Kareta from University of Arizona, who will be talking about telescopic and lab investigations of the surface of active and cometary near-Earth objects. So we'll have all the panelists speak in order, the order in which I introduced them, and then we'll have the Q&A. All the attendees who want to ask their question can do so using the Q&A feature at the bottom of the Zoom webinars software. Do not use the chat feature. And when you ask your questions, please be sure to indicate your affiliation. And also you can upvote other people's questions in order to raise their priority in the queue. We've asked the presenters not to answer questions via text while others are presenting or other presentations are still ongoing. And we'll answer all the questions aloud during the Q&A session, which is after all 4 speakers present. You can also chat with each other if you want through the Slack channel called press_conferences. It's not a default channel, so you'll have to search for it and add it or add yourself to that channel. With that, I'll turn it over to the first speaker.
Hi, thank you, Shantanu. Yes, and thanks for having me. My name is Colin Orion Chandler. I'm a National Science Foundation Graduate Research Fellow at Northern Arizona University. I'll talk to you today about recurrent activity from active asteroid 248370, 2005 QN173. It's a long name. It's a main belt comet. And, I'm on a train, so we hope that this is going to continue to go okay. So a real quick crash course on active asteroids. What are they again? They are asteroids that have tails. So these are objects that are found in the asteroid belt, but they are surprisingly have comet-like tails. So there's asteroid belt, right? That's between Mars and Jupiter. And so this tells us about where water is now. That's useful for things like space exploration, we need fuel, etc. And that's also where asteroid mining might come in. But it also tells us about the long unsolved question about exactly where did the water on Earth come from. So it was believed for a while that it may have all been delivered from external sources, but we know that a good portion of it came with the place when it was born here on Earth. So we would like to know if asteroids are actually a viable reservoir to account for some of the, or a large portion even, of the water that came, that we find on Earth today. However, to know if asteroids are a viable source, we need to find more of these active asteroids. But unfortunately, so far, we've found fewer than 30 of these active asteroids. So this particular story for us starts out when a new active asteroid was announced via Telegram, which is how we play that game in this particular area of the field. And so we get this diagram that says there's a newfound active asteroid, and its location is in this main asteroid belt that's between Mars and Jupiter. It was the discovery was announced in July 2021. It's the object is around 4 kilometers diameter, and its orbital period is roughly 5 years. So we actually have a citizen science project called Active. The brightest about 100 asteroids. So there's a lot of, we reduce that down to about 24 fully processed that for sure have the object in the image that we can see. This is showing all of those images that we found the object in, the little yellow and red circle and V respectively, the direction image only. This in the we see that for sure had a tail in it or activity. So the rest of them, it would either was no activity seen or it was inconclusive. So if we zoom in on that red one, we can see here the active activity is in the form of a tail. It's a long thin tail pointing roughly towards 5 o'clock. This is from July 22nd, 2016. And that's important because that was roughly 1 orbit ago for this object. And so that means that this object was previously active. The image is from the dark energy camera, which is on the 4-meter Blanco telescope in Chile. The observers were Dustin Lang and Alistair Walker. So this image here has the object right in the middle of the center with the white arrows pointing towards the tail. So that's on the, yeah, and that lines up with the arrows there as well. So just through our analysis, we're able to find, again, this object was previously observed to be active. It's the 8th only known active asteroid that's been recurrently active, made of Comet. And it's probably ices that are sublimating that's causing this. This image here shows a follow-up image taken later by Chad Trujillo for Scott Shepard at that same instrument, and it's got a quite very long tail. It's quite impressive. So just to recap, this is we're talking about recurrent activity from this active asteroid 248370 2005 Q173. My co-authors again are Hsieh and Chad Trujillo. We found this prior activity epoch at roughly 1 orbit ago, 2016 July 22nd. It's most likely caused by ice sublimation, and it is likely a main belt comet. So with that, thank you very much. And I hope you heard something.
Okay, we'll have Henry next.
Yep. Okay. All right. Hi, everyone. Thanks for coming to this briefing. So today I'm going to be talking about the same object as Colin, but focusing on a somewhat different aspect of it. So, so I'm going to start with an introduction just to explain a little bit more about what Colin was saying. So asteroids and comets, for those of you not familiar, are supposedly these 2 different types of objects in the solar system. Asteroids are rocky and inert bodies. They basically look like dots when you see them in a telescope. Comets, on the other hand, are icy and active, and this is because when they're ice, when these get close to the sun, their ice sublimates or turns from solid to gas, and escapes and drags out some amount of dust. So this is what causes their fuzzy appearance. In terms of their orbits, asteroids are mostly found in the, sorry. In terms of their orbits, asteroids are mostly found in the inner solar system between Mars and Jupiter. So that's in the main asteroid belt. That's the donut-shaped fuzzy area over there on the left. Meanwhile, traditional comets like Halley's Comet, for example, shown as an orange oval over there on the right. In the zoomed out version of the solar system, they have much more elongated orbits, which causes them to spend a lot more of their time farther from the sun, well beyond the orbit of Jupiter, which obviously makes it easier for them to stay icy, and they only visit the inner solar system very occasionally. So that brings me to active asteroids, which Colin talked about as well. So these are objects that have orbits like asteroids, but show activity like comets. And so on the right there, there's several images of various active asteroids, which are all, as you can see, pretty comet-like in appearance. Interestingly, although comets are classical comets show activity that's always attributed to sublimation, the causes of activity in active asteroids actually vary. Some is still sublimation driven, like in classical comets, but dust can also be ejected when, for example, one asteroid collides with another one, or an asteroid is spinning so fast that it actually starts to partially break apart. So also interestingly, it's possible that activity could be caused by more than one of these factors working together. And as Colin mentioned, the studies of these objects is still quite new, not very much are known, so we're still really excited whenever we find a new one. So this brings me to the subject of the work here, which is, like Colin said, 248.370.2005 QN173, which I'm going to call QN from here on. The orbit is shown as a light blue circle on these diagrams that I showed you earlier. So as you can see, again, like most asteroids, it has a circular orbit in the main asteroid belt and stays entirely confined to the inner solar system. However, earlier this summer, in July, QN, which is, you can see on the left, is the white spot in the middle, was found to have a white tail, which extends down into the right. And this was discovered by the Atlas survey telescope in Hawaii. Atlas observes large areas of the sky every night, mostly looking for asteroids that might hit the Earth, but also tries to look for comets on the side. And so they found QN was active. So this triggered a whole observing campaign. So we kicked off this large observing campaign using 5 telescopes on 3 continents plus Hawaii back in July and August. And our goal was basically just to learn as much about the comet as possible, trying to answer questions like how much dust is coming out, what kind of dust, is the activity getting stronger or weaker, how does it compare to other comets, and so on. So along with this new observing, which actively targeted this new comet, we also searched telescope archives to find times when telescopes serendipitously, which is the fancy astronomy way of saying accidentally, observed the object in the past. So in other words, someone was observing something else and our object just happened to pass through the frame. So this allowed us to study the nucleus of the comet, which is the solid core at the head of the comet, and measure things like how big it is and what it's made out of when dust is not actively coming out, which tends to mess up measurements like this. This is what Colin talked about, but I think he dropped out, or at least for me, he dropped out. So I'm not sure how many of you heard about that, but this is very similar to what Colin did for his work. So I also just wanted to quickly take the opportunity to talk about some major contributors to our work. So we collected a lot of our observations under the Las Cumbres Observatory Outbursting Objects Key Project, or the LOOK project, where Las Cumbres Observatory consists of a worldwide telescope network that gives astronomers near constant access to nighttime observing somewhere in the world. So that gives them their unofficial slogan, keeping you in the dark, or keeping astronomers in the dark, as you prefer. Another cool aspect to this observing that I think is the Fox Telescope project, which runs various outreach programs, but the one that helped us out was Comet Chasers, which gives elementary school students in Wales in the United Kingdom the opportunity to actually use a professional grade telescope to collect real astronomy data. And so big thanks to them as well for their contributions to this work. So, so here are just some results to show you. Here's a gallery of several images where we show archival data when the object was active along the top row. You see that archival data, and the other panel show images from 2021 when the object was active. So as you can see in the later images, we see a pretty nice long tail in the follow-up to the discovery image. So from our analysis of the archival data, we found that the nucleus of the comet is about 2 miles across, or a bit bigger than the length of the Golden Gate Bridge, which sounds big, but is actually on the small side for most asteroids that astronomers typically observe. Just because asteroids are usually pretty far away, so they need to be pretty big for us to be able to see them. So this is, just as a side note, it's a little smaller than what Colin reported, because we actually did some measurements, and that was the size that Colin mentioned was based on sort of previous estimates, basically. So we also found that the tail is about 450,000 miles long, so about 500,000 miles long in the brightest image, but just 900 miles wide. So to put these in perspective, the total tail length is about 3 times the distance from the Earth to the Moon. But if you scale it down to the length of a football field, so like 100 yards, the tail would just be 7 inches wide. So the narrowness of the tail actually turns out to be pretty interesting, because it means that dust is coming off of the comet very slow, so less than 1 meter per second, or slower than most people walk. So meaning that the gas flow is very weak, much weaker than other comets. So the thing is that just like rockets need to reach a certain speed to escape from Earth's gravity, ejected dust needs to escape from the comet's gravity. And so it's possible that such slow dust may need something else to help it escape, possibly something like fast rotation to give the dust a little extra outward push. This is just a hypothesis at this point, though, and we will definitely be trying to test this in the future with additional observations. So with that, I'll end here. A paper about this work was just accepted by Astrophysical Journal Letters. You can get a preprint at the link at the bottom of the slide, or email me for the final version. Thanks for listening.
Next, we'll have Elliot Young presenting.
Hi, everyone. Can you hear me okay?
Yes.
I know that there are guidelines for setting up a background, and I'm sorry, I just gonna go with my home office here. Does the screen show up okay?
Yes.
Okay, let's get to it. Here's why it's a surprise that Pluto's atmosphere is as big as it is and has been growing for the last 30 years. Pluto's perihelion was back in 1989, when Pluto was about 29.6 AU from the sun, and it's been getting farther away from the sun since then. In 2018, it was more than 10% further from the sun. So using the familiar R-squared law, we'd expect there to be over a 20% drop in the flux it receives from the sun relative to 1989. And Pluto's atmosphere, like Mars's, is supported by the vapor pressure of an ice. That's totally unlike the Earth. We don't have a water vapor atmosphere supported by vapor pressure of the ocean, but Mars does have a CO2 atmosphere supported in large part by the vapor pressure of CO2 ice on its surface. Similarly, Pluto, its atmosphere is supported by the fact that there are big deposits of nitrogen ice on its surface, and nitrogen supports a vapor pressure. Now that vapor pressure is a really steep function of temperature. If you turn up the temperature on a piece of nitrogen ice by just 1.5 degrees, you'll double its vapor pressure. On Pluto, that means that if the surface nitrogen ice increases in temperature by 1.5 degrees, you've doubled Pluto's bulk atmosphere. And there have been a few modeling efforts predicting when Pluto's atmosphere would eventually freeze out. This is a figure from Eric Meza's paper in 2019. And you can see the black dots, the observations, show that there's been a steep increase in Pluto's atmosphere over the last 2 decades when we've had occultation observations, and predictions for the atmosphere to roll over anytime now, real soon. In 2018, there were good circumstances for observing Pluto as it moved in front of a pretty bright star, a couple of magnitudes brighter than Pluto itself. So your signal and noise is not impacted too much by photon shot noise from Pluto. And I don't know if you can see my cursor. Can you see the center line up here in this figure?
Yeah, we can.
Yes.
Thanks. So this event was a good one for a couple of reasons. A pretty bright star and a center line that went across the US, so it'd be easy for us to deploy portable telescopes. Let's see, happens at night. And we had the good fortune to have this follow a release of the Gaia catalog and a really good Pluto ephemeris, as you might expect if a spacecraft just flew by Pluto. So we had a prediction for this center line, and around Virginia and around Texas, we deployed about over a dozen portable telescopes. And we used low read noise, fast readout CMOS detectors that had built-in GPS chips so that we could get good timing without a lot of extra effort. These two sites here in Lake Corpus Christi State Park and down at in Alice, Texas, were really close to the center line, as were some of the sites in UVA, and that was a little bit unprecedented. We've never gotten that close to the center line before, and we've never gotten a central flash as strong as the Lake Corpus Christi event. I wasn't planning on talking about where central flashes come from, but if there are questions about that, I'd love to touch on it briefly. Let me just say, though, that the strength of the central flash peak drops quickly as you move off of the center line, so that the relative strengths of two of the central flash peaks from two sides of the chord give you really accurate location with respect to your cross-track error. So two things were kind of remarkable. One, the prediction was really good, 12 kilometers. It wasn't long ago where we'd be happy to be within 100 kilometers of the prediction, much less 12 kilometers. And the Lake Corpus Christi telescope was 6 kilometers south of the center line. In other words, really close. So our picket fence, I'd say, worked out pretty well. Here's what happens as you look at your light curve, what you observe from the occultation, and you change the surface pressure or you change the haze opacity. To first order, we observe a lot of U-shaped curves. The star moves, the planet moves in front of the starlight drops, and then it comes back. If you've got a central flash, you'll get a peak in the middle. And if you change the surface pressure, the shoulder of the light curve is easy to discriminate. It doesn't get affected much by haze, and it lets you do an initial estimate of the surface pressure. I want to point out a caveat. If you're in the occultation business, there's been a history of using the half-light point as a proxy for the surface pressure. And at least in the case of Pluto, it turns out that's a mistake. If you change the surface pressure, you get 3 different light curves, but they all cross here. And so the half-light point doesn't discriminate surface pressure very well. So I encourage people to stop doing that. The haze opacity, once you know the surface pressure, it turns out that the central flash amplitude is really sensitive to haze opacity. So that works out well too. Here's the fit that we get for surface pressure. Ingress and egress were a little bit different. Combined, we get a minimum chi-square residuals at a surface pressure of 11.4 microbars. And for comparison, New Horizons in 2015 measured 11.5. We measured a one-way optical depth to the Hsieh of 0.024. That's a little bit higher than the average optical Hsieh that was measured by New Horizons, although they had a factor of 2 difference between the northern hemisphere and the southern hemisphere. So if the trend of Pluto's surface pressure had continued the way it was going for the past 25 years, we should have seen 14.4 microbars in August. Instead, we see basically the same thing that New Horizons saw. And it's for the first time, it shows that the trend is reversing. And I feel this is pretty robust because we've got, really good location and a lot of high signal to noise light curves. We wondered if there was a correlation between Hsieh opacity and the solar cycle because of coincidental correlations. In 2002, there was a lot of Hsieh opacity. It dropped by more than a factor of 30 the next time we looked at Pluto in 2007, and that correlated with a drop from a solar peak to a solar minimum, and we wondered if that was continuing. And at least these last 2 observations, 2015 and 2018, don't support that. The solar activity decreased, but we observed a slight increase in Hsieh opacity. And that's it. Thanks.
Next, we'll have Teddy.
Okay. Hi, everyone. So I'm going to be talking about a project today that sort of formed the backbone of my PhD thesis at the University of Arizona, though as of Friday, I'm now a postdoc at the Lowell Observatory. The title of my talk is Telescopic and Laboratory Investigations of the Surfaces of Active and Cometary Near-Earth Objects. So topically, this is closer to the first 2 talks you heard about today. So I'm going to be talking about, the origins of the Geminid meteor shower, which you can see in a couple months in the middle of December. We're going to be talking about the object that made it 3200 Phaethon and a possibly related object, 2005 ED, and some really, really interesting laboratory work we did to heat rare meteorite types up to try to understand the physical properties of these objects and maybe understand how the meteor shower was made. This paper was published 2 weeks ago today in the Planetary Science Journal. And if you want to email me, I can get you whatever version you like. So Phaethon, 3200 Phaethon, is the parent body, meaning that it made the Geminid meteor shower. But unlike other meteor showers, it doesn't really look or act like a traditional active comet. It's blue in color, which is rare by asteroid standards and not really known of for comets. Its orbit gets really, really close to the sun, maybe like a comet, but it has a generally asteroidal orbit otherwise. So it gets really warm at its closest, but it never really gets that cold. And it's not really active. It loses some mass. It does develop a tiny little tail, but it's not enough to make the meteor shower that we all know and love. So the question is, we look at an object with these strange properties, and you can see this artist rendition on the right. And we understand, how did this produce the Geminids? Why is it currently inactive? And how does it relate to other objects we want to compare it to? We're going to go visit it with a spacecraft. The JAXA, the Japanese space program, is going to visit it in the late 2020s, which I'll talk about in a bit. But it's really interesting that we're going to be able to go and explore an object that breaks a lot of the conventions that we know about how meteor showers are made, and learn a lot, with one hopes, in the way. One of the most interesting things that we can do to prepare for the spacecraft visit and understand this object in the meantime is to study an object called 2005 UD. 2005 UD is in a very similar orbit to Phaethon. It has a similar blue surface color, again rare, and it's smaller. I've scaled these two 2D images to be approximately the same size. It's tiny, and if you look out at papers in literature, what people are saying, they say that 2005 ED is a fragment of Phaethon. So at some point, Phaethon tossed off a chunk, which we now call 2005 ED. So the question is, are they really related? There's been a few interesting papers and some interesting discussion over the past few years that maybe says that their orbits are similar, but not perfect. We want to understand the relationship because it turns out that Destiny Plus, this JAXA spacecraft, might be able to visit not just Phaethon later this decade, but also 2005 UD. So what observations can we do now to understand how these objects are really related, how they compare? And one thing I will also mention is that another similarity that these two have is that while 2005 UD is smaller, it's blue, it's in a similar orbit, it also is inactive and it also has a meteor shower that created. There's a lot of similarities between these objects. So starting in 2018, we obtained the first near infrared spectra shown at the left of 2005 UD. You can see that on these plots where wavelength is on the x-axis and reflectivity is on the y, it sort of looks like a straight line sloping upwards. We would call that red. And on the right-hand side of the screen, you can see 2005 UD in black compared to Phaethon in blue. If these two objects had similar surfaces with similar surface properties, we would expect these curves to look very similar. But you can see Phaethon's is curved, it's downsloping, and 2005 UD's is upsloping and roughly linear. This is a really challenging discrepancy to explain, and it's the first measurement that's so concretely showing that these objects don't look very similar in all the ways we know how to observe them. This was a special circumstance. It took a long time and a lot of hard work to get these observations. But this is the first time that someone's observed it in the near infrared, and especially with spectroscopy. So the question is this so big a discrepancy that now we're saying these objects maybe aren't related, and maybe Destiny Plus will be seeing two different kinds of objects that sort of produce meteor showers, maybe in similar ways, maybe in different ways. We want to understand their relationship. So one idea that we had was that they're made out of the same material. These two objects started from the same point, but because they're both on these orbits that get them so close to the sun, well inside the orbit of Mercury, maybe they've been heated to different extents. So just like if you put toast into a toaster and you take it back out and cool it back down, you can tell it's been toasted even if it's cold now because it's changed color. That's what we're talking about here. The problem is that the existing laboratory data of people heating meteorites to higher and higher temperatures didn't go hot enough to be able to match the extreme conditions that these asteroids go through. So the solution is that we spent part of 2019 and a good part of the pandemic building and then using a new laboratory device where we put a sample of a meteorite, a powder, which you can see on the right-hand side of the screen in the one labeled A, in a little sample cup. We then put it inside a sealed chamber, pump it down to an almost vacuum. We were trying to emulate outer space, and then heat it all the way up to a new temperature, cool it all the way back down, and then get a reflectance spectrum to see how it's changed. On the far right-hand side of the screen, you can see a picture of the sample cup glowing because it was so hot. This is taken when it was almost as hot as it got. This is like if you go camping and you have a poker and a fire and it starts to glow red. The hottest temperature we got the sample up to was actually about 2,000 Fahrenheit or about 1,000 Celsius. So really hot. It took a lot of hard, long, safe work, and don't worry, we were good, but it's really interesting. So what we did is we watched it change with temperatures. We heated it up, cooled it back down, and looked to see how it changed. And you can see all that here. The scale is not the same as the plot I showed you before. I just wanted to get you an idea of what we were up to. We were heating at increments of about 50 Celsius. So basically just doing it a little bit, cooling it back down, and seeing those changes happen gradually. And if you heat this meteorite, and we got a sample of the Hsieh chondrite or gay on loan from the Vatican meteorite collection, so thank you very much to them. If you heat it up to a Phaethon-like temperature, you can get it to look quite like Phaethon. Not perfect, but close enough to be really interesting. The same cannot be said for 2005 UD. So to be clear, we had one last idea for how these objects could still be related, even though they look so different using this new technique, and it didn't pan out. But we think we learned a lot more about Phaethon and perhaps about the composition of the Geminids along the way. So in summary, we got the first near-infrared observations of this proposed mini Phaethon, this tiny little object, this clone of the thing that made the Geminids, and it doesn't look similar using the techniques we used. We created this new data set of heated meteorite samples that I think both help us understand these objects and should be useful to people studying things that get really close to the sun in general. And we don't think we know how to explain the difference between these two objects. We think they have to be They share their similarities by coincidence, but there are differences we cannot reconcile. So that's all I have to say. Email me if you have any questions or want a copy of the paper that was just recently published. Thanks.
Okay, thank you to all the speakers. All the panelists can turn on their webcams again, and we'll take questions. So if you have any questions, you can ask them in the Q&A box, which is at the bottom towards the right of your Zoom interface. So far, we have one question. And when you ask your question, please mention your affiliation as well as who the question is directed towards. So the first question we have is from Robert Adler. I'm guessing it's directed towards Elliot Young. And he would like to know what causes the central flash in his observations of Pluto.
It's a good question. It's different from the familiar diffraction spot that you might see, the Poisson spot or the spot of Arago. It's not a diffraction effect, it's a refraction effect. And basically what's going on is Pluto's atmosphere acts as kind of a poor lens. It takes incoming rays and always points them towards the center. And there's going to be some altitude in Pluto's atmosphere where the bending angle is just right so that by the time you hit your telescope, 34 astronomical units away, you've bent and traversed about, well, Pluto's radius. And that altitude for Pluto is actually pretty close to the surface, probably tens of kilometers, not hundreds of kilometers off of the surface. This, by the way, could be a useful thing to know about for exoplanet transits also. Generally, central flashes let you probe lower in an atmosphere than if you didn't have them. You know, often your light kind of peters out at millibar levels, but central flashes might let you probe down to microbar levels, so you can get a little bit deeper. There's one more interesting factoid about central flashes. Can I take 30 more seconds? I just want to spread why they're so great. One thing that is interesting is central flash shapes are really sensitive to oblateness. If you've got a planet that's a fast rotator and it's a little bit fatter at the equator, the central flash will have a diamond-shaped caustic. It won't be a circle or anything like that. It'll have pointy features. And if you have telescopes that cross those features, you can learn a lot about the figure of an atmosphere. And this was used to great effect by Bruno Saccardi and Bill Hubbard for Titan. And they noticed that when they had a bunch of chords crossing the central flash, that they would see actually a 6-pointed caustic, and they deduced that there were fast winds on Titan at about 50 degrees north and 50 degrees south. It wasn't just an ordinary oblate atmosphere. There were some fast zonal winds that distorted the atmosphere at certain latitudes, and that was kind of a neat trick.
Okay, next question is for Henry Hsieh. It's from Hal Weaver from JHU APL, and he asks, what albedo did you assume when deriving the size of the nucleus of the active asteroid?
Yeah, thanks, Hal. So we just used the neowise measured albedo, so that's it was 5.4%. So this is so the diameter that Colin quoted was also from neowise. So we got a slightly, when we did the archival data analysis, we got a slightly fainter absolute magnitude. So that's the reason for the smaller size, but we use the same magnitude. And this is what you'd expect for, C-type asteroid. So it's yeah, so it kind of made sense. But yeah, we just used that 5.4%.
Thank you. Next question is from Rick Lovett. He's freelance and he asks, how much vapor are these active comets losing over the course of time, including billions of years? Obviously not enough for them to totally desiccate. Is it significant loss, however? Yeah, I'm guessing this is for him.
Colin, do you want to take a stab at it? I mean, I can, but I just answered one.
I think I'm better than you go. I'm just going on Road City.
I don't know how Colin's connection is. Might be
I think he wanted you to handle it, Henry, because he said he was going under a city.
Yeah. Oh, I see. Yeah, I mean, that's a really great question. And it's a question we would really like to know the answer to as well. It's probably very low. Usually the mass loss rates are about like 0.1 kilograms per second, which is pretty small. So, and they're only active over a short portion of their orbit. So, yeah, so they probably don't lose a lot of mass each time, but like there's a lot of uncertainties. Like we don't know exactly how long the duration is. The production rate probably varies during that active period, and then it depends how many times, how many orbits they're active over, which we also don't know, because we've only been observing these things over a relatively short period of time, like 15, 20 years or so. So there have been thermal models that kind of try to estimate the amount of ice that's lost over each orbit period. But again, there's a lot of complications because we think the ice is probably stored below the surface because that's the only way they could survive over billions of years. And so they might need to be activated for that ice to actually start to sublimate. And so if you only activate like a small portion of the surface, like that ice goes away, but the rest of the surface, just remains icy. So yeah, so there's lots of complications, but we think it is physically possible for ice to remain over a long period of time. So that's not so surprising, but we want to figure out the details, of course. Thanks for the question.
Okay, next question we have from Rachel Berkowitz, American Physical Society. This one's for Elliot Young. How should the changing surface pressure / change in warming trends show up in terms of Sputnik Planitia and other surface ice? Is there a connection to be drawn here?
Yes. Do you mind if I share my screen just for a second?
Go ahead.
So this might be faster. This comes from Perry Ann Johnson's paper, and it's an example of what happens if the albedo or the emissivity or the subsurface thermal inertia changes. How does it affect the time evolution of surface pressure? And you can see that they all make a difference in terms of how high a pressure you'll get before Pluto's atmosphere starts to freeze out, and a smaller difference in when that peak happens. Rachel, I'm afraid I've forgotten the exact wordage of your question already, but I think it was how does the time evolution of surface pressure translate into knowledge of subsurface things like thermal inertia? And this is supposed to be an example.
I guess the exact question was how should the changing surface pressure and change in warming trends show up in terms of Sputnik Planitia and other surface ice?
So I don't think Sputnik Planitia is going to go anywhere. It's such an enormous reservoir. But a key question is, where do you have condensation sites elsewhere on the planet? Where is it cold enough for you to have condensation? And that locations where you have condensation or not, that's a big difference. A little bit, all you have to be is a little bit warmer. your vapor pressure just needs to be a little bit higher than the ambient pressure, and you will not be a condensation site. And so if we could resolve Pluto and make albedo maps to see where new frost is getting plated out, or even better yet, temperature maps, that would be pretty interesting. And there may be a possibility of getting useful resolution, useful enough to get tens of elements across Pluto with ALMA, and those would be temperature maps. So I think that's an interesting course of study to pursue in the next coming years. I don't think Sputnik Planitia is going anywhere. A related question is what kind of convection is slowly going on underneath Sputnik Planitia, and how does that affect its effective thermal inertia? But it's not going to sublimate away. It's just way too big. Thanks.
Okay, next question is from Camille Carlisle from the Sky and Telescope. This is for, I believe, Colin and Henry. What observations would be key in determining the cause of these asteroids' activity?
How's your connection, Colin?
In the chat, he says
sorry,
he's on a train.
I didn't hear the question. I didn't hear the, so what observations the cause of asteroid activity? Well, one important piece is if it's been recurrently active or not. You able to hear me okay?
It's a little choppy, but yeah.
So if it's been active more than once, yeah, I mean, Henry can say more, but if it's been active more than once, it's likely not something like a one-off event. So recurrent activity is one of the most important.
Yeah, I think it's still a little choppy. Yeah, basically what Colin said. So recurrent activity, which is what his work was about, was is like a pretty, we think is a pretty solid indicator of whether sublimation is causing the activity, because just like regular comets, we expect every time they come close to the sun, they heat up, and so this is a very natural way to explain activity that happens every single orbit. Whereas if it's something like an impact, you don't expect an impact to happen like at the same spot in the orbit, you know, multiple orbits in a row, for example. For the fast rotation, we just need to check if it's rotating fast. And so that would be done by observing the object when it's not active, like I mentioned. And then we can get what's called a light curve, and we can see how it changes its brightness as it rotates. And from that, we can determine how fast it's spinning, and then, you know, do some basic physics, and, you know, figure out whether it's above or below the critical limit for, you know, for breaking apart. Yeah, and we can do other things like the spectroscopy that Teddy was talking about, where we can see what the composition of the surface is and see if it's consistent with material that contains ice or is completely dry. So there's various things we can do. So it runs the whole gamut of spectroscopy and just imaging. Yeah.
Okay, thank you. Another one, this one is about Pluto from Rick Levitt again. What is delaying the freezing out of the atmosphere? For Elliot Young.
Hi, thanks. That's really the basic question. And the answer is there's got to be subsurface residual heat. It's kind of the same effect as why the sand on the ocean is probably hotter in the afternoon than it is at high noon, or why the hottest time of year is probably August or September as opposed to the solstice. There's residual heat that's stored under the surface, and it keeps the surface warm even for the few decades after perihelion. And looking at exactly when the rollover in pressure happens gives us an idea what that thermal inertia must be. How porous is the subsurface? What's its specific heat? How does it hold on to to heat. And so it's kind of a rare chance to look below the, the few millimeters that we usually see and try and understand something below the surface. So the short answer, heat stored underneath the surface that propagates upward even when the sunlight is decreasing.
Okay, thank you. And it looks like that's all the questions we had. So I'd like to thank all the speakers for their presentations, and I'd like to thank the audience for joining in. There are 2 press releases from today's conference, and the link, you can find links for them on the Slack channel if you join it. And I would like to thank all the PIOs who helped with the press release and the briefing preparations. And finally, thanks to USRA for sponsoring the press activities at this conference. You'll be able to access these presentations on the AAS Press Office YouTube channel. And we'll see you tomorrow again at 11 a.m. Eastern Time, 8 a.m. Pacific. And we'll have 4 more talks tomorrow. So thank you and see you again.
Thank you.